Not all worlds are created equal. Some are cold, some are barren, some are scorched or frozen or stripped of everything that could sustain anything alive. We have found thousands of planets beyond our solar system, worlds of every conceivable size and temperature and composition, and most of them are hostile in ways that feel almost familiar. Too hot, too cold, too close to their star, too far. Hostile in ways we can name. But there is a category of planet, rare, extreme, extraordinary in its violence, that goes beyond hostile in any ordinary sense. Planets where the danger is not just the absence of something life needs, but the active, relentless, multi-layered, physics-driven presence of something that destroys. Planets where every single feature of the environment, the temperature, the pressure, the chemistry, the radiation, the winds, the very material falling from the sky, is tuned as if by some malevolent design to eliminate anything that dares to exist within it. We have found several candidates, but one stands above all others. One planet, confirmed, studied, measured in detail by the most sophisticated instruments we have ever built, earns the title without contest, the deadliest planet ever discovered. And what makes it truly extraordinary is not just how it kills, it is how many different ways it kills simultaneously, each one operating independently, each one sufficient on its own to be lethal, together forming a layered, comprehensive, almost elegant system of destruction that leaves no margin for survival of any kind. Its name is WASP-12b, and by the time this story is finished, you will understand why no list of dangerous worlds comes close to placing it anywhere but first. WASP-12b was discovered in 2008. It orbits a star called WASP-12, a Sun-like star approximately 1,400 light-years from Earth in the constellation Auriga. And from the moment astronomers began analyzing its properties, it was clear this was not an ordinary world. WASP-12b is a hot Jupiter, a gas giant roughly twice the size of Jupiter in our own solar system, with a mass approximately 1.4 times Jupiter's. Enormous, bloated, its atmosphere puffed outward by the intense heat of its nearby star. How close is it to its star? Its orbital period is 1.09 Earth days, 1 day and 9 minutes. That is how long a full year lasts on WASP-12b, the time it takes to complete one orbit around its star. For context, Mercury, the innermost planet of our solar system, the closest planet to our Sun, orbits in 88 Earth days. WASP-12b completes its orbit 80 times faster than Mercury. It is so close to its star that the surface temperature on its day side, the hemisphere permanently facing the star in its tidally locked orbit, reaches approximately 2,900 degrees Celsius, nearly 3,000 degrees. Hotter than the surface of many stars, hotter than the melting point of every known material, every metal, every mineral, every compound we have ever studied. Tungsten, the element with the highest melting point of any pure metal used in the filaments of light bulbs precisely because of its heat resistance, melts at 3,422 degrees Celsius. WASP-12b's day-side temperature approaches that threshold. On this planet, rock does not exist as rock. It exists as vapor, iron, silica, titanium, vaporized, rising in clouds of metallic gas through an atmosphere so hot that the very concept of solid matter becomes irrelevant. But the temperature is not what makes WASP-12b uniquely, extraordinarily lethal. It is what the star is doing to it. WASP-12b is so close to its star, so impossibly, recklessly close, that the tidal forces between the planet and the star are stripping it apart. The star's gravitational pull on the near side of WASP-12b is significantly stronger on the far side. This differential, this tidal gradient, has stretched the planet into an egg-shaped, not spherical, egg-shaped, tidally distorted, pulled toward its star like taffy being drawn toward a fire. And material from the upper atmosphere, gas from the outermost layers of this already enormous, already bloated planet, is being pulled off and into orbit around the star, escaping the planet's own gravitational grip and spiraling inward toward the stellar surface. WASP-12b is being consumed, slowly for human standards, catastrophically for astronomical ones. Scientists estimate that WASP-12b is losing the equivalent of roughly 6 billion tons of mass every second to atmospheric escape. 6 billion tons every second. At that rate, the planet has a projected remaining lifespan of approximately 3 million years before it is entirely consumed by its star. 3 million years sounds like a long time. In human terms, it is almost unimaginably long. In astronomical terms, for a planet that has likely existed for billions of years, 3 million years is nothing. A rounding error. The last few seconds of a very long life being spent falling into a fire. WASP-12b is a world in the final act of its existence, being devoured by the star it orbits, losing its atmosphere in a continuous plume of escaping gas that stretches toward the stellar surface like a river of planetary death. And we are watching it happen in real time. Let us descend into WASP-12b's atmosphere. Not physically, not literally, but scientifically. Layer by layer, using the spectroscopic data collected by Hubble and other telescopes that have studied the light passing through this planet's atmosphere as it transits its star. The upper atmosphere. In the uppermost layers of WASP-12b, temperatures are somewhat lower than the extreme dayside surface, but only by comparison. Still thousands of degrees, still beyond any material threshold we recognize. Here, astronomers have detected water vapor, not liquid water, not ice, superheated water vapor existing at temperatures where the molecule is constantly being dissociated by the intense radiation, broken apart into hydrogen and oxygen atoms, and reformed continuously in a chemical cycling driven by the energy pouring in from the nearby star. They have also detected carbon monoxide and carbon dioxide. And most remarkably, they have detected evidence of carbon in ratios suggesting WASP-12b may be a carbon-rich world, a planet with a different fundamental chemistry from Earth, where carbon rather than silicon forms the dominant chemistry of whatever solid material might exist deep within the planet. Carbon worlds are theoretical, or were theoretical. WASP-12b is the closest thing we have observed to one. In a carbon-rich planet, the deep interior might not contain silicate rocks as Earth does. Instead, it might contain graphite, carbon under extreme pressure crystallizing into diamond, a planetary interior made partially of diamond under conditions of such extreme pressure and temperature that even diamond, the hardest naturally occurring material we know, becomes uncertain. A planet with diamond layers being slowly consumed by its own star. Going deeper. As you descend through the atmosphere, pressure increases rapidly. The hydrogen and helium that compose the bulk of the planet's mass become increasingly dense. At sufficient depth, hydrogen transitions into a metallic state, the same exotic, electrically conducting liquid hydrogen that exists deep inside Jupiter and Saturn. But here, under WASP-12b's extreme conditions, that transition happens shallower, faster, in a planet so hot and so compressed that the phase boundaries between gas and liquid and metallic hydrogen blur into something our models struggle to simulate accurately. The winds. Driven by the enormous temperature difference between the permanent day side facing the star, blazing at 2,900 degrees, and the permanent night side facing away, cooler but still thousands of degrees, the winds on WASP-12b move at extraordinary speed. Models suggest wind speeds of several kilometers per second, supersonic, planet-girdling, driven by a heat differential that makes the most extreme weather on any other known planet look tame. These winds carry vaporized metal, vaporized rock, the disassociated fragments of whatever molecular chemistry survives in the upper atmosphere, swept from the scorching day side toward the relatively cooler night side in a continuous planet-scale circulation. And above all of this, permeating everything, irradiating everything, the stellar radiation. WASP-12b receives roughly 7,500 times more stellar radiation than Earth receives from our sun. 7,500 times. The ultraviolet flux alone would destroy any complex molecular chemistry within moments of exposure. The X-ray emission from the star, striking WASP-12b's atmosphere at close range, drives the atmospheric escape, energizing the upper atmospheric gas and giving it enough velocity to overcome the planet's gravitational pull and stream away into space. The star is literally boiling the planet away. And every single feature of this environment, the temperature, the pressure, the chemistry, the radiation, the winds, the tidal forces, the atmospheric escape, is lethal. Not in a scaled, graduated way, not in a more or less way. Absolutely lethal. Completely. Without exception or mitigation. This is not a world that is merely hostile to life as we know it. This is a world that is hostile to matter itself in any form we recognize. WASP-12b is not scientifically valuable despite being lethal. It is scientifically valuable because it is lethal. In the extreme, the physics becomes clear. In the ordinary, the processes are modest and overlapping and difficult to isolate. But in a world pushed to the absolute limit of what planetary physics allows, a planet being eaten by its star with an atmosphere of vaporized metal, orbiting in just over one Earth day, every physical process is operating at maximum intensity. And at maximum intensity, everything becomes measurable. Everything becomes detectable. Everything leaves a signature in the light. Studying WASP-12b has taught astronomers things about hot Jupiter atmospheres, atmospheric escape, tidal interactions between planets and stars, and the chemistry of carbon-rich worlds that simply could not have been learned any other way. The detection of water vapor in WASP-12b's atmosphere was one of the first confirmed detections of water in an exoplanet atmosphere, a milestone that proved the technique of transmission spectroscopy worked, that we could actually read the chemistry of alien worlds in the light of distant stars. That technique, validated on WASP-12b, is now being applied to more promising worlds, to potentially habitable planets around nearby stars, to the atmospheric signatures that might one day tell us whether life exists elsewhere. WASP-12b made that possible. The study of WASP-12b's tidal stripping, the visible, measurable loss of its atmosphere to its star, has refined our understanding of how planets lose their atmospheres over time. This matters for rocky planets too. Earth-sized worlds orbiting close to active stars are subject to the same atmospheric escape processes, though at far less extreme rates. Understanding the physics in WASP-12b's extreme case helps us model what happens to more modest planets in more moderate circumstances. And WASP-12b's brief remaining lifespan raises a question that haunts every planet hunter who thinks about it carefully. How many WASP-12b-like planets have already been consumed? How many worlds in the 13.8 billion year history of the universe have spiraled inward toward their stars and been absorbed? How many planetary graveyard stars are out there, holding the math of absorbed worlds in their outer layers with no remaining evidence of the planets that once orbited them? The answer is almost certainly many. Hot Jupiters are thought to migrate inward from their formation locations in the outer regions of their solar systems. This inward migration, in some cases, ends in consumption. The planet spirals too close, the tidal forces become too strong, the atmospheric escape becomes catastrophic, and eventually, the planet falls into the star entirely, adding its mass to the stellar material and leaving no trace but a slight change in the star's surface composition. WASP-12b has a 3 million year countdown. It is not the first planet to face this fate. It will not be the last. And knowing this changes how we look at the night sky. Every star we see might once have had more planets than it does now. Planets that migrated too far, orbited too close, and were slowly, inevitably, consumed. The universe is not just creating worlds. It is constantly, patiently, destroying them too. WASP-12b is 1,400 light-years from Earth. It will never threaten us. It will never reach us. Its star is not our star. Its fate is not our fate. In 3 million years, when the last traces of WASP-12b spiral into the stellar atmosphere of WASP-12 and disappear forever, nothing about Earth or our solar system will be directly affected. It is safe to contemplate from a distance, but it is not safe to contemplate without consequence, because every extreme world we study is, at some level, a mirror, a reflection that shows us what we have by showing us what others lack, what we are protected from by showing us what is possible when those protections are absent. Earth is 150 million kilometers from our sun, not 3.4 million kilometers the way WASP-12b is from its star, not so close that our year lasts a single Earth day, not so close that the tidal forces pull us into an egg shape and strip our atmosphere into space, not so close that every molecule of our atmosphere is being dissociated by radiation and swept away by supersonic winds. Our sun is warm and stable and moderate. WASP-12 is similar to our sun, but WASP-12b's proximity makes all the difference. The same kind of star, but a planet placed in the wrong position, and the result is not life, but the most comprehensively lethal environment we have ever found. Position is everything. Distance is everything. The difference between a world that can sustain 4 billion years of evolving life and a world that is being eaten alive in a blaze of vaporized metal and tidal forces, the difference is simply where you are relative to your star. Earth is in the right place. Not by an enormous margin, not with vast reserves of safety. The habitable zone around our sun is relatively narrow. Slightly closer and we might share Venus's fate, a runaway greenhouse effect that turned a potentially habitable world into a 465-degree acid bath. Slightly farther and we might share Mars's fate, a world that lost its atmosphere and its oceans and its warmth to the slow freeze of insufficient sunlight. We are in the middle, in the right place, and WASP-12b, blazing, dying, being torn apart by its own star 1,400 light-years away, is a reminder of just how precisely, how narrowly, how consequentially that placement matters. The deadliest planet ever discovered is not a cautionary tale about some alien world. It is a reminder about our own. A reminder that the conditions we live in, the moderate temperature, the stable orbit, the gentle tidal forces of a distant moon, the protective magnetosphere, the liquid water, the breathable atmosphere, are not the universe's default setting. They are the exception, the rare, improbable, astronomically fortunate exception. WASP-12b is what happens without the exceptions. It is what the universe produces when the conditions are wrong, when the distances are off, when a world ends up where it should not be. A planet that burns and tears and escapes and falls, performing a final million-year death spiral into the star that made it. There is something almost tragic about it. A world that might have once had a quieter existence, farther from its star, before orbital mechanics and tidal interactions drew it inward to its fate. We will never know whether it began differently. We only know how it ends. In fire, in pieces, in the slow, inevitable consumption of something that has lost its distance from the thing that both gave it energy and is now taking everything else. And 1,400 light-years away, on a small blue planet in exactly the right place, we are watching, learning everything we can from a world that has nothing left to lose. And perhaps, in the quiet moments, after the data is processed and the papers are written and the science is done, feeling something that has no technical name, something that looks, if you tilt your head at just the right angle, a great deal like gratitude.